We've just had the Bailey House dinner, as some of you will recognise from the colour of the balloons I've got here, and they were full of helium. So I thought it was too good an opportunity to miss, so I brought some of the balloons to the laboratory with me, and I thought we'd do some experiments on the acoustic properties of helium. So the first thing we'll do is breathe in a little bit of helium. Not an experiment I recommend you do at home, but let's see what happens. So if I talk, my voice has gone a little bit higher, and the more helium I take, if I take a bit more helium, my voice becomes a bit squeaky, which is really rather silly. But I think you might have tried this, and it all goes a little bit squeaky. And I've looked on the internet for a good explanation of this, and all the explanations I've seen are not very good. So we'll do a few more experiments and see if I can explain it using physics apparatus. So I've got myself here an old milk bottle, and some of you know if you blow over the top of a milk bottle, you get a note. And what I thought it might be quite interesting to do was to put some helium in the milk bottle. So I'll take one of my balloons, just going to cut it off. Here we go. And fill the milk bottle with helium and see if it makes any difference at all. So I've never actually done that experiment before. I just thought it up the other day to see if I could use it to show you what happens. And I don't know if you've noticed, but once the helium was in the glass milk bottle, to begin with, the note was actually slightly higher. And then as the helium dispersed, the note went lower and lower, even though it's the same milk bottle and it's me blowing in the same way. And it's this effect that explains why your voice goes a little bit higher when you breathe in helium and then try and talk. So let's try one more experiment. And again, genuinely, these are experiments. I've never done them before. I was just desperately trying to think of a way to explain this phenomenon to you. This is a little organ pipe, a little flute from a church organ. And rather better than me blowing over the milk bottle, it plays a note. And that note is dependent upon its length. So I've no idea what will happen, but let's blow it in air and then try it with some helium gas. So I need another balloon. So here we go. I'll just cut it off like that. And cut the end off the balloon. Okay, I think we've got that note. So let's have a helium organ. That's really quite remarkable. It doesn't last very long, but whilst the helium is in my mouth and I blow through the organ pipe, you certainly hear the note going slightly higher. So, same organ pipe, same blowing effect over what can be considered to be the lip or the reed here, which makes the gas vibrate. It's just the gas inside the pipe that causes it to change its note. And I think that's really interesting. So there are a few of my videos where I've spent a short amount of time trying to think of a good explanation for you. You might want to look on the internet about why does my voice go squeaky when I breathe in helium, and you'll be truly amazed at the utter rubbish that's out there. All sorts of things, even on relatively learned sites, which are completely wrong. Now, I'm not suggesting I'm going to give you the whole story today, but we've simplified my mouth and the cavities inside my mouth and the vocal cords to an organ pipe, or even simpler, just a milk bottle. And so that's limited our variables. And what we found is the one thing that affects the pitch is the gas. And we know something about helium. We know that helium is much less dense than air. One of the reasons that if you don't tie down helium balloons at a party, they disappear off and stick to the roof. And helium gas is actually much lighter than air, which is a mixture of nitrogen and oxygen mainly. And what that means is that sound can travel much faster through helium gas. The particles aren't bonded in air, or at least between each molecule, and they're not bonded in helium gas either. They're freely moving around. But they're much lighter, and they pass the sound wave much quicker. So the first thing to take on board here is that sound travels through helium about 3 times faster than it travels through air. Sound goes through air at about 320 meters per second, and it goes through helium at atmospheric pressure and normal temperature at about 970 meters per second. So the speed of sound in helium is 3 times faster. So now for the final part of the explanation. When you take an organ pipe, this one has a fixed length, and therefore it has a fixed natural frequency. That one. The same is true of the milk bottle. It's a slightly different length, and therefore will have a natural frequency that's different. The shorter the organ pipe, the higher the natural frequency and the higher the note. And those great big huge organ pipes have very low natural frequencies and play very low notes. Now, when we played with this, one of the things you need to know is that the velocity of sound is equal to its frequency times by its wavelength. And if you remember, the velocity in helium gas is about 3 times faster than it is in regular air. But the pipe stays the same length, and that's crucial. So the wave that builds up in here will have a fixed wavelength. That's governed by the length of the pipe. We could consider this one to be sealed at this end and have air vibrating a great deal at that end, so you would get a quarter wave fitting onto it. So the wavelength that would fit into this type of pipe is 4 times the length of the pipe. But it's a fixed wavelength. So if velocity equals frequency times wavelength, if the wavelength is fixed and the velocity on the other side of the equation goes up, then the frequency must go up. So it's really a lot easier than some people are trying to make out on the internet. This lip here doesn't change when I put helium in, neither does the top of the milk bottle. So simply, your vocal cords don't change either. The size of the cavities inside your mouth, which have natural frequencies, don't change either. So the only thing that does change is the velocity of the gas. It's 3 times faster. So if the wavelength space that's resonant remains the same, for the velocity to go up on one side of the equation, on the other side, the frequency must increase. And that's why your voice goes squeaky. So I hope you enjoyed that video. It was great fun making it, and would you believe it's snowing again outside? So I hope you've learned quite a bit about helium and why your voice goes really silly when you breathe in rather a lot of helium. I've enjoyed making it, and when my voice sorts its life out, I'll be teaching again next week. See you then.